welcome to my last lecture, which we will talk about the first order theory related to convex analysis. Let me start with the topic. Okay, so first order theory, what does it mean? So first order relates, first order means some kind of derivative, but normally when you're on a manifold or you're on a linear space, you can simply talk about derivative or differentiation. But in this, since we are in geodesic space, or more specifically, we are in the kappa spaces, there is no notion of differentiation or how to find derivative. So we have to come up with something that can replace that concept. And okay, there is an aim that this notion of the first order or the replacement of the derivative should reduces to the classical derivative on manifolds and at the same time on a linear space. Actually, there were some attempts by, as far as I knew, there were two papers that kind of construct the first order theory of monotone operators in this setting. And in those papers back in 2017, one of them is mine, by the way. In those papers, we kind of use what we call the dual space to cat zero space. But it turns out that that notion was not so good in the sense that it will only reduces to the classical notion of when you are in a Hilbert space. But when your cat zero space is a manifold, there is no relationship between this new concept in 2007 and the classical concept in Riemannian manifold. So that was not so nice. Okay, what we want to do is we want to recover all the cases. We want to unify all the theory within this framework. And this unification was one of my paper published earlier in this year. So it's not in any book for now. So it's quite a modern way to consider this. But earlier I discovered that this concept was used, actually not the first order concept, but the concept of tangent space where we build our theory upon, was used earlier in 2015 by Ota and Palfier, but they were considering a different thing. So it's not an overlap, but just an elementary tool that was used before. Okay, so before we get into the main topic, we need to give you some revision. Firstly, we need to recall the notion of a pseudometric. And secondly, we need a construction called a Euclidean cone over a metric space. So let me recall first what a pseudometric is. So suppose we were given an anonymity set where I will call this set M tilde. Okay, then a function d tilde defined on this M tilde cross product with itself into 0 to plus infinity. Then this function is called a pseudometric. On this m tilde if all the condition, all the properties of a metric hold except that d of x, y equals to 0 does not necessarily imply that x equals to y. And here x and y belongs to the set m tilde. Okay, so it is a relaxation of a metric space. Okay, a relaxation of a metric space. M tilde can be any set, just like a metric space. And the function d tilde is a function that satisfies all the metric conditions, except for that when you have distance between x and y being 0, you cannot claim that x and y are identical. Okay, in a metric space, if you have the distance between 2 points being 0, then you can simply say that x and y are identical. But in this case, no. When you have the 0 distance between x and y, you cannot just claim out of nowhere that x and y are identical. Okay, so if D satisfies all the metric condition except for this condition, you call it a pseudometric. Sorry, this has to be D tilde. Okay, now the pair m tilde and d tilde will be called a pseudometric space. Pseudometric space. Okay, I should add then here because otherwise you will not know what d tilde is. So if M is any set and d tilde is a pseudometric on M tilde, then this pair will be called a pseudometric space. Okay, this is one notion that you need to bear in mind. And okay, so back to this board a little bit. So I write tilde here and also tilde here in the function because finally we want to create a metric space out of this m tilde d tilde, out of this pair. Okay, so finally we will create a metric space out of this. Such a process is called metric identification. So what is a metric identification process? So suppose that m tilde d tilde is a pseudometric space okay, then we define we define a relation called tilt, okay, on M tilt cross M tilt, no, on M tilt. So given by, we say that x is similar to y, so this is a kind of similarity relation. X is similar to y if and only if the tilt between x and y is 0, and of course this is defined for any x and y on M tilt. Okay, so this relation tilt defined by this is an equivalence relation. Okay, so equivalence relation means this relation is reflexive, it's symmetry, and it satisfies the transitivity condition. Okay, so you can see quite easily by using, reflexivity comes from a property of a metric, of a pseudometric, sorry. Symmetry comes also from the symmetricity of the pseudometric, and the transitivity comes from the triangle inequality. Okay, so it's not so difficult to see that this is an equivalence relation. And when you have an equivalence relation on a metric space, you can create another metric space. This is not a metric space, this is pseudometric, but you can somehow. You can define what is called the quotient metric space. So the quotient space M defined by M tilt mod with this tilt relation, and this is nothing but the set of all equivalent classes X tilt, where X belongs to M tilt. Okay, and just to recall you, this equivalent class here is defined by the set containing all the points Z such that X is similar to Z, right? Or in this case, in other words, you have the point Z in M tilt such that the pseudometric between X and Z is 0. Okay, so let me continue on that board. So M there is just the set containing all the equivalent classes created from the relation, from the equivalence relation tilt. We use a lot of tilt here. We will use a lot more, don't worry. Okay, so equivalent class, okay. Then we want to define a metric on that quotient space. So the function d given by D of equivalent class of X and equivalent class of Y, defined to be D tilde of X and Y. This is well defined. So this is actually a set. This is actually a set, but if you take any elements from this set and you plug it here, for example, X itself has to be contained in this equivalence class as well as Y. So you can take X and Y here and put it in D tilde. Okay. And this is the value for this distance between two equivalent classes. If you take other representation from this and this, suppose, for example, if U is inside this and if V is inside this, so you have X tilde equal to V tilde and, sorry, U tilde, and Y tilde equals to V tilde, and if you choose U and V instead of X and Y and put it here and here, then still you get the same value coming from the fact that this is an equivalent class given by D tilde equals to 0. Okay, so this is well defined. No matter what representation you choose from these two classes, you get a consistent value here. You will get the same value here. So this is well defined. Okay. Oops, sorry. And this has to be true. This is defined for every equivalent classes from M. Okay, so this function D here, given by this, is a metric on M. Okay, so in other words, MD is a metric space. So you can see that we can create a metric space out of a pseudometric space quite naturally, in fact. And in practice, when you do other kind of construction, usually the bracket is left out, or at least the tilde here is left out. We don't write this and this. So it's kind of have a simpler form. When you have a specific one, we don't really need to specify everything, and the notation will look cleaner. Here you might think things can be a little messy or tricky. Okay, so this is the metric space created from pseudometric space, and the process is called metric identification, constructed from a pseudometric space. If it's clear from the content, we don't really need to say that, okay, it's created from M tilde and D tilde and so on. Okay, another creation, another construction is the Euclidean cone. A Euclidean cone over a metric space. Okay. So here you are given a metric space MD, not necessarily this one, okay? Not necessarily this one. Any metric space, okay? Just any one M and D. Actually, this is the definition. The Euclidean cone over MD, let's say over M, is defined by C0. So C here is a cone, and 0 here denotes the Euclidean term. Okay, so Euclidean means you have 0 curvature. So C0 here is the Euclidean cone. Actually, you can take C kappa, which is the kappa cone. We don't use that here. Okay, so I will just restrict ourselves to the case of C0 or the Euclidean cone. Okay, so C0 of the space M, okay, is defined by okay, you have the product space M and R plus. Okay, let me write it in this way. Okay, metric space M and no, not like this, product. Okay, so M and non-negative real Cartesian product together. This is mod with another equivalence relation. We have two of them. Okay, so I will always write double tilt here, where so how do we define this double tilt? We define it like this. Okay, maybe we require some space, so I will erase. Oops. I think this is too similar to an X, so smaller. Okay, Cartesian product of M and the non-negative reals, and this come back. Okay, this double tilt is given by this. It's given by, okay, we have elements from M. I will denote it with X, and T is similar to Y and S, if and only if we have two cases. So the first case is T and S are identical to 0. Okay, so the first case, we don't care about X and Y. If both T and S are 0, then they are equivalent. Or, okay, T and S are identical, but not 0. And another thing is required is X and Y are equal. Okay? So the equivalence relation is defined by this relation. Xt and Ys are similar if and only if either the two parameters T and S are identical to 0, and or otherwise T and S are identical and non-zero, and at the same time X and Y are the same. Okay, of course this have to be defined for every Xt and Ys from M times this interval. Okay, so I will note that this relation is an equivalence relation. Moreover, so if the diameter of x is less than or equals to pi, exactly pi, okay, no curvature involved, then we have rho of x and t. This is an equivalent class defined with respect to this double tilt, okay, and ys. Okay, this is defined by t squared plus s squared minus st okay. Okay. So rho here, which is of course defined for every x and t and y and s. Can you see? Is it possible to close the shade a little? Thanks. Okay. Okay, so we define rho like this. Rho between equivalence class of xt and another equivalence class of y and s is defined like this. You have a big square root, and inside this big square root you have t squared coming from this, plus s squared coming from the second one, minus 2st, so s and t, cosine of the distance between x and y. Okay, so every component here will play a part in this definition. Okay, so s and t, x and y, and this have to be defined for every pair of equivalent classes. Of course, these equivalent classes are coming from C0 of M, because if you come back to this board, C0 of M is actually the quotient space of this product mod with this double tilt. Of course, elements inside this are equivalent classes with respect to this double tilt, and okay, of x from M and t from this interval. Okay, so you define rho like this, and then what you get here is that then this function rho is a metric on z0 of M. Okay, or in other words, C0 of M with rho is a metric space okay. So the construction is quite long, and actually it's quite complicated. I restrict myself to only the case where diameter is less than or equals to pi. Actually, this is not the restriction to define a metric. if you have a diameter of x which is larger than pi, then you can still define a metric, and you have another case. Okay, so depending on the distance between x and y, but we will not use that case in our applications. So I will just restrict to the case where the diameter of x is less than or equals to pi. In that case, you can define a metric on the Euclidean cone like this. Okay, and if you really look at this definition, okay, so the distance on x here should be some kind of angular metric. Okay, that's not forced to, but if you really want to interpret the definition, you have to think of the distance on x as some kind of some sorts of angular metric. Okay, and what else should I say? Okay, and the distance here defined with this formula is inspired heavily from the cosine law, or the law of cosine. Okay, you can see that this is actually the law of cosine. If you square another side, it's the law of cosine. And if you can see that if x and y are equal, s and t are equal, then you have t squared here, s squared here, which is equal. So you have like two t squared, then minus 2t squared again, and cosine of x and y are 0, so this is 0, so cosine of 0 is 1. So you have 2t squared minus 2t squared is 0 inside the root, so it's 0. Okay, if you'd like to see a little bit of how it is computed. So that's the simplest case that you may try. Okay, and what we are going to use in our application is, first we will have a pseudometric space, and then we take a quotient, we get a metric space, okay, by the metric identification process. And after that, we will take a Euclidean cone over that quotient space. So it's equivalent class after equivalence class, and that can be kind of tricky when you look at it from, if you look at it only symbolically. But actually, the idea behind that is quite trivial. I would not say it's easy, but well, the idea is not difficult, but the math behind is quite complicated. Okay, and why do we need all of these? It's because we don't have the tangent space. When you are in a Hilbert space or in linear space, the space is very nice. You can do computation like addition or scalar multiplication and so on. So you have everything there. When you step outside that territory into a manifold, into a smooth manifold, I would say, or a Riemannian manifold, what you can do is you can approximate locally points on the manifold with its tangent space. So a tangent space is always a Euclidean space. So what you do there, you just simply project locally the points on a nonlinear surface onto a Euclidean space, and you do all the computation on the Euclidean space, and then you project back to the manifold. That is what's happening, and that's why in manifold you can do lots of things, because you have a very, very good calculus. But in this case, we are in a situation, in an uneasy situation, I would say. Things are quite complicated. We don't have calculus, we don't have anything. So how can we come up with kind of tangency? Okay, so normally you can simply define the tangency or a normality using calculus, but here you don't have anything of those. So we have to overcome these difficulties. The idea is very obvious. You want to define a tangency, the idea of tangency, but how to come up with tangency without calculus. That is the source of complication here. Okay, so how do we define? Actually, this is not my definition, okay? People from geometry has used this long time ago, so it's not my creation. I just took it and used it. Do we need anything else? Yes, we need one more. Now we are back into cat-kappa space. Okay, we are back into cat-kappa space. Okay, let me say it like this. Actually, this notion works for any cat-kappa space, but I will only restrict myself to the case of kappa equals to 0. Okay, because in applications that I have, I don't know about kappa being positive. It's still open. There is no result. Okay, so let me go back to cat 0. Let me say cat 0. We will need the notion of an Alexandrov angle first. As I said, we want to come to Euclidean cone here. And when you have this kind of thing, it's quite natural that the distance on x should be some kind of angular distance. So that's exactly what's happened here. I want to use the Alexandrov angle as an angular metric. Actually, an Alexandrov angle is not a metric. It's a pseudometric. So we need to identify the resulting metric space first in order to take the Euclidean cone over that, and we obtain another metric space that we can work with. Okay, so here always I suppose that xd is a complete cat 0 space. Actually, in some of the notion, we don't need the completeness, but for simplicity, we will just assume completeness here is a complete cat 0 space. Okay. We fix a point P inside the space and and let GP be the set containing all normalized geodesic with let me call it C, normalized geodesic C with C0 equals to P. Okay, so it's like this. So suppose this is X, some surface. You have X here. And from this point X, you can have a geodesic to any other points as you like. Okay. So you take all of these geodesics and collect it here in GP. I have to add one assumption that this geodesic is non-constant, so all non-constant normalized geodesic. So what does non-constant mean? Non-constant means the start point and the end point are different. Okay, we don't consider constant geodesic which does not go anywhere. We will only consider the case where the endpoint is different from P. Okay, so this is the set GP. And for any C1, and let me call it gamma and sigma in GP. The Alexandrov angle between them is given by, so Alexandrov angle is denoted with alpha for Alexandrov, alpha at P, okay, because this is from GP, and you can imagine that if you move the point P, here around, then the space GP will change, of course, because it's the start point. So GP is defined for each point P in the space. So alpha P between gamma and sigma is defined by limit as S and T tends to 0 of this. I will state later what this is, okay? Okay, so gamma T bar and sigma T bar where the triangle P bar, gamma T bar, and sigma S bar is a comparison triangle of the triangle P, gamma T, and sigma S. Okay, and this we have to make assumption that S and T are positive. Okay. So what are we really doing here? Is we want to define an angle between two geodesics. So suppose this is the point P, and okay, we have gamma and sigma. Gamma may be this geodesic, okay, with some endpoint, we don't know what, but this is gamma. This is sigma, another geodesic, and we want to know what angle it makes, because the geodesic is not a straight line, it's not a line segment. So the angle between them have to be defined carefully, because okay, if you have a straight line segment making a wedge at some point, then it's not so difficult to find the angle between them, right? You just take your any tools you want and you just measure it. But here it's kind of curve. So what is the angle here? How to define them? If you are on a manifold, what you will do here is you take the derivative of gamma at 0. You take the derivative of sigma at 0. That will give you two, okay, suppose this is a manifold first, okay? So you take a derivative of gamma at 0, you got a vector. You take a derivative of sigma at 0, you get another vector. Let's call this, and this is sigma dot 0. Okay, so you have you have two vectors, and you just measure. These vectors are a straight line segment, right? Straight line segments. So you just measure the angle between two line segments. This theta will be considered as the angle between these two curves. Good. So do you see the tool here? We take the derivative. that is manifold. That is very nice, but we don't have that luxury here. Okay, so we cannot take the derivative. If we can, then everything is simple, but we cannot, unfortunately. So we have to use the concept of Alexandrov measuring the angle between two geodesics. And it's measured like this. The angle between gamma and sigma is defined to be the limit as S and T tending to 0. Of course, it's 0 from the right. Okay, and what you do here inside the limit, let me write it on another board. Okay, so suppose we have P, we have, okay, gamma, we have here sigma. We take any intermediate points on sigma and on gamma and on sigma. So suppose you have here gamma T and here sigma S, okay. S and T are from the open interval 0 to 1. Sorry, I did not write this correctly. So S and T belongs to open interval 0 to 1. Okay, so we have the point P, we have the point gamma T, and we have the point sigma S. And then this is a cat zero space, okay? So you can have a geodesic connecting these 2 points as well. Okay. So now you have a small geodesic triangle. You take this geodesic triangle and, okay, this is X, and you construct on, this is cat 0, okay, so M2 0 is R2. So you construct a comparison triangle on R2. So P bar is here. This is sigma S bar. This is gamma T bar. Okay, and you have the similarity between the two triangles. Okay, and this is in R2, so you can measure this angle, right? This angle is what I wrote, the angle bar at the point P bar to this to these two vertices, so gamma T bar and sigma S bar. You can measure the angle just on R2 just to specific the point that two lines are making the angle and the two other vertices. Okay, so you have this, and if you really want to compute this, it's really easy. You can just take, okay, what is this? This is arc cosine of norm of gamma T bar minus P bar times the norm of sigma S bar minus P bar divided by the product between these two vectors. Okay? Okay, so note one thing, we don't include the constant geodesic, so that gamma T bar and P bar cannot be the same point, sigma S bar and P bar cannot be the same point, so that you won't have zero divisor. Okay, so this is well defined again with this formula if you want. So you have the angle here on R2. Okay? And now what you do, you move these two intermediate points towards the point P. Okay, now we come back to X, okay? We fix T, we fix S. We get these two intermediate points. You create a comparison triangle. A comparison triangle is a kind of projection, if you'd like, okay? But it's not really a projection, okay? So you have two similar triangles. Okay, so you take this, you create a comparison triangle here. You measure this angle with this formula. You get one quantity, one real quantity, positive or zero, okay, non-negative. And what you do here is you move, you decrease T and you decrease S, so that these two intermediate points will move closer to the point P. And when you move these 2 points closer, you have another triangle, geodesic triangle, maybe like this. Okay? So you take this smaller triangle, geodesic triangle, and you create another comparison triangle for these 3 points and measure again the angle. And you keep doing this by taking T and S going to 0. So these two intermediate points will tend towards the point P, and you will obtain the limit. We can somehow show, this is quite technical now, so you can somehow show that this limit actually exists, okay, under the assumption that X is a complete cat zero space, okay. This limit always exists because when you move S and T, when you decrease the value of S and T, the value inside the limit also decreases. Okay, so it's a kind of monotonical limit theorem that you want to use, so the limit exists. Okay, and I have to note here that even though we move gamma T towards P and sigma S towards P, and we get a kind of smaller geodesic triangle here on X, it does not mean that you have a comparison triangle that is a part of this big comparison triangle with this larger S and larger T. So the comparison triangle will change and will not fit here. Okay, it most probably occur that this angle will, okay, it will be smaller, sure, but the angle here will also decrease. Okay, so it's not moving linearly like this. It's not moving like that. Okay, when you decrease this, you have to make sure that you create the right comparison triangle in order to measure the new angle that is occurring. And you move S and T towards 0, you will get the Alexandrov angle between two non-constant geodesic emanating from the same point P. Now here comes a very important theorem. Okay, the theorem says alpha P, the Alexandrov angle defined like that, is a pseudometric on GP. Okay, so you have the pseudometric on the set GP. So you have a pseudometric space. Now here comes a definition. The space of direction at P is the metric space obtained is the metric space S and SP and angle P. Okay, obtained by the metric identification of GP and alpha P. Okay, so it's quite clear that alpha P is not a metric, but it's not so clear that it's a pseudometric. Okay, that's another story. It's quite clear that it is a pseudometric because you can find two geodesics for which alpha P between those two geodesics is 0, but the two geodesics are different. You can just like take this point P, you take any geodesics, let's call this gamma, and you take another geodesic halfway of gamma, and you call this sigma. Okay, and if you compute alpha P here of gamma and sigma, of course it's 0 because it does not make any angle. Okay, it's 0. If you construct a comparison triangle out of these geodesics, you will always have a degenerated triangle, which means it looks like a line. So this is one side. Suppose this is U and V. So U and V is one side, and if you have W here, another side is UW, and another side is WV. So we have kind of three sides, but it degenerates into a line segment. And if you measure the angle UW and UV, of course, through this formula, you have 0. Okay, so alpha P is not a metric, but it is a pseudometric. Showing that it is a pseudometric is another story. It's quite technical. Okay, so now we have a pseudometric space, GP alpha P. And next, what do? We take the space of direction, we take the metric identification of this pseudometric space. The metric identification will be denoted with another notation, namely SP. Okay, so SP is elements inside this is equivalent classes of non-constant geodesics. Okay, equivalent class means this is a class containing all the geodesics that make 0 Alexandrov angle with gamma. Okay, and this is just a renaming of alpha P. We prefer to use this notion. Okay, and this is the space of direction, which is a metric space, of course, because it's constructed by taking the metric identification. So SP and this angle P is a metric space. Moreover, let me close this first part with this theorem. Okay, the theorem is very simple. This space, this metric space, is a cat1 space. Okay, it preserves the class of Alexandrov space, but the curvature bound is changing. So actually, if X is any cat kappa space and you do this kind of thing, then the space of direction will always be a cat1 space. Okay, no matter what kappa you take on the first place. Okay, so that's for this first part. Let's have a 5 minutes pause, and then we'll come back to our construction. Okay, now we have the first metric space created from taking the metric identification process from GP and alpha P. What's next? Okay, we simply take the Euclidean cone over this metric space, and we get the tangent cone. I will explain the intuition behind all this once we reach the tangent cone, okay? So we are like one definition away to our ideal tool. So the tangent space at P denoted by TPX. Many people will drop this x and many people will include this x. I prefer to include, because actually what is this? It is the tangent of x. Okay, if x is some surface, then what is this tangent to? It's tangent to x, but at the point P. So I prefer to include x here. So TPX and DP is the metric space defined by let me write it here. So TPX is nothing but just the Euclidean cone over the space of direction. Here is just direction, we just, no one will write x here, okay? Okay, so TPX is defined just to be the Euclidean cone over the space of direction there. So what is this? I erased it already. Okay. Okay, so I will just rewrite it again just to recall it for you. So this is the space SP product with this interval, and we mod it with this equivalence relation. So elements will look like, okay, elements from SP, which is an equivalent class of gamma with respect to this, right? This is distance, the pseudometric is 0, so the pseudometric is the Alexandrov angle. So class of gamma means the set of all geodesics which has 0 Alexandrov angle with gamma. And another number, okay? So it is equivalent class after equivalent class. But we will simplify this once we finish this definition, okay? So what is this? This is equivalent class of this pair, which means either if you have another one, let's say class of sigma and S, when will these two elements coincide? Either S and T are both 0, or both S and T are the same but non-zero, and at the same time the class of gamma and the class of sigma are the same class. So what does it mean? It means you have the same direction and the same length towards that direction, you consider that the same, you consider that to be identical. Okay, so I will come back to this. Okay, here is the space, and now the distance, of course, actually when we say it's created from taking the Euclidean cone over this metric space, the distance of TPX is clear because before we used the term rho, but here we will use dp because this space will change with p, so we have to indicate what point are we working on at the moment. So dp, I will just follow what I wrote earlier, but just adapt to this this definition, this particular definition. So for now, I will write this complicate one first, okay? Okay, so this is the big square root of t squared plus s squared minus 2s t cosine of the Alexandrov angle, but now made into a metric on the space of direction. The angle of what? Of gamma and sigma. Okay. Okay, so here we have the space. Elements are written like this, and we have the distance between two classes, two elements. Quite complicated and messy and tricky. So in the future, I mean the future towards the end of this course, okay, that future ends there. So the future, we write okay, so first thing, we will delete this tilt. Okay, this tilt is the tilt coming from the angle being 0. Okay, this is the first tilt, and we will delete it. And we will just delete the second bracket entirely. But we have to, this is the abuse of notation, right? This is the abuse of notation because actually when we delete the bracket, it's an element inside this equivalence class. But actually we will treat this without the bracket as the equivalence class itself. Okay, so this is quite abusive, but that's more convenient. Okay, so I will just write gamma here because we tacit this class already, and t. This is to be this class given by that itself. Okay, so we have this simplification. We have this simplification. And we have even further simplification for some particular elements of the tangent space. we will denote this 0p to be the class when t is 0, okay? And I will write gamma p x dot, just like the derivative at 0, but actually it's not. But we will write this equivalently to that derivative. It denotes the class given by gamma px and distance between p and x. Okay, for any x inside x. So what is gamma px? Gamma px is the normalized geodesic joining p to x. One thing. Actually, this is also an abuse of notion because when p and x are equal, then this is 0, but this is gamma pp, and gamma pp actually does not belong to gp. gp is non-constant, the set of non-constant geodesic, and gamma pp is not in gp. Therefore, we don't have the class of gamma pp inside the space of direction. Okay, but just the abuse of notation. Okay, when p equals to 0, when p equals to x, the dpx equals to 0, and we will claim that it will reduce to 0p here. Okay, with a lot of abusive. And here gamma px, just to recall that gamma px is the normalized geodesic joining p to x. Okay, so actually we require p not the same as x in order to define this class. But of course, if p equals to x, this is 0, and we come back to this case, we don't care about this thing anymore. Okay, we don't care about this class anymore. Okay, so now we have the tangent space, which is the main tool of the first order theory. And we have a theorem here. Of course, we know that this is a metric space by some results from the Euclidean cone over a metric space. But the theorem here says that the tangent space Tp and dp is a cat0 space. And we have a big remark here. So even when x is complete, we assume the completeness from the beginning, but actually we don't really need that up to now. But even when x is complete, SP, angle P, and TPX, dP are not necessarily complete. Okay, this is a big remark. And I will show you in a moment after I explain the intuition of the space of direction and the tangent space. Okay, and if you want to work with complete space, you can take the completion of the space of direction and of the tangent space. Okay, so you will call the final product there the completed tangent cone, because this is not necessarily complete, and if you take the completion here, then you will call it the completed tangent cone. Okay, so next let me explain to you the intuition behind all of these complicated concepts. The idea is quite simple actually, but the mathematics behind that is not so simple. So suppose you have a space like this. Let's begin with the easy one. So suppose this is the surface of your space X. Okay, and you take any point P. First step, we want to construct GP. GP is the set containing all normalized geodesic non-constant emanating from P. So you have geodesics to everywhere, to every point. Okay, and then you take the first bracket. Okay, what does it mean? Actually that means you want to consider the direction of the geodesic, not the geodesic itself, but you create a direction from that geodesic. Okay, so suppose you are considering this geodesic, this curve. What you really do is you just turn this curve into a direction. Okay, it goes on forever. This whole line, not elements inside, okay, it's not like this, but you consider this whole line as one element, and this is kind of direction. You don't know how far it goes. You just say, okay, we are going to that particular direction. And this direction is created from this geodesic gamma. So suppose that this is gamma. What is this? This is understood to be this kind of direction. And no matter how far you go, suppose you have gamma here, and you have another one, you have, let's call it sigma, going halfway here. It's still in the same direction. Just the distance towards the endpoint are different, but it's still in the same direction. So you consider these two geodesics to have the same directions. And actually, if the space is not so well behaved, you will have another geodesic with different endpoints, not on the same line. Okay, different endpoints like different like this. Okay. Not like this on lying on the geodesic. So you can have another geodesic like this, but finally the angle between these two geodesics, let's call this beta. Okay, these two geodesics can have 0 Alexandrov angle. That can happen. Okay, that is the singularity that can happen in this space. And when you have this kind of thing, you will again consider the curve gamma and beta to have the same direction, because it makes 0 Alexandrov angle between them. So you consider it to have the same direction. You don't know how far it goes. You consider this as one element. And very often we will consider this to be a kind of unit direction. It does not force to be, but we like it that way. So instead of considering this to go as far as we want, we consider this to end to be this particular direction with unit length. Actually, we don't really talk about length, but we can somehow regularize the idea or normalize the direction to be the unit. Okay, so going in this direction, and the representative is the unit direction. You do this for every possible geodesics. You get all the possible directions that you can go from this point P, and in this case it will look something like a circle, right? I mean, the end of the arrow will be like a circle. And if the space is not like this, suppose the space is, okay, it's this kind of surface of the sphere. Okay, and you have a kink here. You have a kink, and you have another smooth surface. Okay, so suppose it's not smooth like this, but you have kind of kink. So you have kind of kink here. Okay, I cannot draw very nice, so that's my demonstration. Okay, this is not a smooth manifold. You cannot define the tangent space or the space of direction classically using the calculus because you lose the smoothness here. But still you can use this kind of notation and you can define, okay, you have geodesics, and so on. So your space of direction will somehow look like this up to this point. And then maybe I cannot draw nicely, sorry about that, but maybe you have a kind of kink also in the space of direction. Actually, you don't have this line. This is the direction itself, but you can have a kind of kink on the line here. This is the space of direction. So let me write it as SP. Next, we take the tangent cone. Sorry, we take the Euclidean cone over SP, and that will result in a tangent space, or someone will call it a tangent cone. What do you do? Actually, this is just the direction without telling how far to go. The idea is very simple. You have the direction already. You just add how far you want to go. That is the meaning of the second component in the product. The idea is there. You tell me the direction, and you tell me how far you want to go into that direction. Okay, but to regularize the idea, to make this a metric space, to make this a cat zero space, and so on, you require this complicated construction. Okay, it's not as simple as it looks, but this complication works very, very well, and it's very natural once you get to know it. So you have the direction already. Now you tell me how far you want to go. You want to go this far. You keep it. This is one of the tangent vector. I call it vector, but it's not actually a vector. You want to go shorter. Fine, have this. So it depends on t, on the second element here. This can be t, right? Okay, if t is small, you have a shorter vector. And if t is 0, you're not going anywhere. That is 0p. If t is large, okay, it continues this way indefinitely because we take the second component is taken from the non-negative real line. And if you take that t to be exactly the distance between p and x, and the direction is the direction at p towards x, then it's a kind of projection from, okay, if this is x, then you kind of project this curve onto this direction. The idea is very similar to the manifold, but on the manifold you just take the derivative, but here you have the complicated, purely metric construction. And when I say it's complicated, it's really complicated, and the proof is very, very technical. But it works. Okay, so this is the idea. And also for this. Now, why I say, even when x is complete, the space of direction and the tangent space can be incomplete. So we can take a really, really simple example. I will take a unit ball. Okay, this is a unit ball centered at the origin of R2, radius 1, closed. So this is, you take this subset of R2 and you embed it with the restriction of the Euclidean distance. So the distance is computed using the straight line, like this. This is a complete cat zero space. Okay, now what? Now I take any point P at the boundary. So maybe I have to emphasize this a little bit, otherwise you will not be convinced. Okay, still not a circle, but better. You can see the curve more clearly. Okay, let me take a point P here. Actually, you can take any point on the boundary. What is GP here? So GP will be the geodesics that goes inside. Okay, it goes inside like this. It goes also to the boundary itself, but you will never get. Okay, so since this is kind of straight line, because this is embedded with the restriction of the Euclidean distance. So if you take a point here, you make a geodesic which is a straight line, you just normalize it. So this is the direction that you get. Okay, if you take this point, this is the direction that you get. Okay, the length of each vector is 1. It's kind of having a unit ball moving to this point, but only for the vectors that will coming from the geodesics that join P to some points in this set. And you will never reach how to say. Okay, so if I take this P to be particularly the point -1, 0, then the tangent line of this circle is this straight line. The equation of this line is x equals to -1, right? This is quite simple. X equals to -1. You will never get an arrow that touch this line, that is exactly on this line, because when you fix a point T here and you pick another element x inside this ball, you have a slight angle from this vertical line. Okay, this slightest angle will come towards this straight line, but it will never be on this straight line. Okay, and you can see that this is isometry to a half circle without the endpoint. Okay, the endpoint is excluded. It's isometry to this, and this is not complete. Okay, and if you generate the tangent space out of this space of direction, you also get an incomplete metric space. Okay, so this is a very simple example showing that even when you have a complete cat0 space, the space of direction and consequently the tangent space can be incomplete. That's what can go wrong, because on a manifold, the tangent space is always a Euclidean space, and that is always complete. So that's one thing that can go wrong. Oops. Okay. Now we have the tool. Let's get back to the theory, the theory of first order. So first order means a kind of derivative. Excuse me. First order means a kind of derivative. And what you want to do here, you want to relate to a convex optimization problem. And so you have a convex function. In general, you can talk about, I mean, in manifold or in Hilbert space, you can talk about gradient of f. You know, when the function is convex, the gradient is always a monotone operator. Since it is linear, it is positive definite. Positive semi-definite. And okay, what happens when f is not differentiable? when f is not differentiable, you have another tool which is called the subdifferential, right? It's a kind of derivative, but it's the set value derivative. So that is what we can do here, because we cannot take the derivative of f. You don't have gradient, you don't have the notion of differentiation. So at best, you can talk about subdifferential. Okay, so always suppose that f defined on x into minus infinity up to plus infinity is convex, proper and lower semi-continuous. Okay, now we want to define a subdifferential for this function. Sorry. A vector, as I told you, is really not a vector, but I call it a vector. A vector v bar, okay? No, not good. I have to fix a point first. Let x bar, no, let x be a point in x, a vector v inside the tangent space at x is called a subgradient of f at the point x if the following inequality holds. So you have fy being larger than or equals to f of x, because we are considering at a point x, okay, x comes here, plus I will define this later, okay? So fy is larger than or equals to fx plus, I call this a product. It's a kind of generalization to an inner product. Fy is larger than fx plus v gamma dot xy, and this has to hold true for all y in x. And the set df at x defined to be the set of all subgradients of f at x. Okay, don't follow me. Okay, so fy being larger than or equals to fx plus product between v and this. Okay, and I have not defined this just yet, and it will go, actually I want to write it there, but maybe here will be better. So this comes to this box, okay? To clarify, maybe we need p here, but I personally don't write this, but just to clarify. So the product p defined on tp x times tpx into real is defined by, okay, if you have gamma and you have, sorry, so you have gamma t gamma t and sigma s this is defined to be st cosine of angle at p between gamma and sigma. Okay, it's defined like this. Of course, for all gamma s, gamma t and sigma s in tpx. Okay, so it's defined like this, and if you reduce x to a Hilbert space, this is the usual inner product. And if capital X is a manifold, then this is the Riemannian metric. The Riemannian metric is an inner product. It's not a metric. You call it Riemannian metric, but actually it's an inner product. But an inner product on the tangent space, I forgot to say this. If X is a Hilbert space, then TPX here is isometry to the space X itself. Okay, when X is a Hilbert space, TPX is isometry to X. When X is a Riemannian manifold, then TPX here coincides. Coincides means it's isometry to the Riemannian tangent space. Okay, the classical way to define a tangent space on the Riemannian manifold. It will be just identical to this TPX defined purely with the metric term, complicate one as before. So this is the product that will replace an inner product on Hilbert space, it will coincide, and replace the Riemannian metric on Riemannian manifold. So this approach is totally a generalization, the real generalization, to both Hilbert space world and to the manifold world. As I mentioned, the tool that has been used before back in 2017 by myself and another people are not generalization of the case when X is a manifold. It will reduce it to the classical theory when X is a Hilbert space, but not when X is a manifold. But this approach is completely unifying both Hilbert space and Riemannian manifold. This definition belongs to our paper. Our paper means myself, Kosaka and Kamame in this year, 21. You may think this is quite complicated, and is this a right result? Actually, we posted this result 2 years earlier before its publication in arXiv, and another person to use this approach was Nicola Gigli from Pisa, and he was very well known for this kind of theory, and that is one of the confirmation that I think this approach works well. Another person who I really trust and also working in this approach, but he has not published any paper just now, but very soon I think, but we have discussed, and they also used this approach, was Genaro Lopez Acido from Sevilla. Okay, so this is just the definition, but this definition really works or not depends on the subsequent results. Where's the eraser? Okay, here are some nice properties. And all the result here comes from the same paper. So let me call it CKK21. Me, Kosaka and Kam-aim 21. Okay, so what do we have? First, we have the domain of this is dense inside the domain of F. So dense means if you, okay, I will say in simple words that when we take the closure of this and closure of this, they are the same. Okay, actually this is a subset of this. Domain of this means the set where the subdifferential is non-empty. Okay, so this is the definition of a subgradient. This is the definition of the subdifferential. Oh, this set here is called a subdifferential. Okay, so the subdifferential, okay, I have to be here. So subdifferential of the function f at the point x. Okay, as you can see, it is a set-valued map, and v is defined to satisfy this inequality, which is not so clear will hold or not. So if there is no vector v such that this inequality holds true, then this subdifferential can be an empty set. And when you have an empty set, you've got nothing to work with, and this definition goes two ways. Okay, so we just need to make sure that the subdifferential is non-empty on a sufficiently useful set. So here comes the first result. So the domain of f here means the point where f takes finite value. Okay, when f takes infinite value, those points we just throw them away. They are no use of consider the value plus infinity. We don't take care of them. We just throw them away. So domain of f means the set containing the points where f takes finite value. So that are the meaningful place where we study. And it turns out that the domain of the subdifferential, which means the set where the subdifferential is non-empty, is dense inside this domain of f. Okay, so it means when we take the closure, they are equal. In other words, if you speak in the language of genericity, that means if you just close your eye and just randomly point to a point inside the domain of f, then with probability 1, you will find the point where the subdifferential is non-empty. Okay? So the probability of randomly pick a point from the domain of f and you will find subdifferential being non-empty is 1. So that's first confirmation that, okay, this subdifferential is a good tool. You can work with this without any too much caution. The next property is the Fermat's rule, still holds for this. So you have the point x minimizes the function f if and only if 0x, remember this vector, this spatial vector, 0x belongs to the subdifferential of f at the point x. Okay? So this is how you recover the first order optimality condition of a convex function with this kind of tool. We also have the relationship between this first order thing and the props. That's also nice. So okay, so we write it like this first. So TV, no, not good. t times gamma dot x y, and by this we means the vector defined by the class of gamma xy, and how far it is t times the distance between x and y. Okay, so this particular vector belongs to the subdifferential of f at the point x if and only if x is exactly the prox of f with parameter t of y. Okay? Next, we can show that this is a monotone vector field. Okay, I don't want to go into vector field, so this is monotone. Monotone in what sense? If you are familiar with monotone operator theory, then this is the same. So monotone here means if you take a point, if you take 2 points x and y, you have gamma dot xy here, and here you have v is less than or equals to u. This is less than or equals to minus of v and gamma dot yx for all for all x and y inside the domain and all u inside the subdifferential of x at x and all v inside the subdifferential at y. Let me see if there is anything else. Okay. Let me mention, okay, this is monotone, and actually it is maximal monotone. Let me strengthen it. So the condition here is the monotonicity, and this is not contained in a graph of other. Finally, we have to use the word vector field. So monotone vector field, monotone means satisfying this inequality for every x, y, u, v like this. And vector fields means the set valued map mean a set valued map, let's say t, from x into the power set of union of t p x, where t coming all over x, such that t of x, okay, here is p, so I will use tp, such that t of p will value only inside the tangent space at the point p itself. So it kind of, if you have a surface, you have p here, TP will be the set of some tangent vectors at the tangent space at that point only. Okay. And these are kind of nice properties that you will get out of this kind of structure. We have a very, very interesting case. It will be strange if we talk about subdifferential and don't talk about normal cones. So if C is a subset of X, it's non-empty, closed, convex, then the normal cone of C at the point X is defined to be the subdifferential of the function of the indicator function of C at X. And if you do the computation, this will simply means you take all the tangent vector V at the point X such that V with X, Y. So this means, remember the definition of this product is the product, the formula is involving the cosine. So actually it's this one being negative means it makes an obtuse angle. So V is here and X is here and XY, this is gamma XY, is making an obtuse angle. Okay, it makes an obtuse angle with elements, with vector that points inside the closed convex set. And you have lots of cautions about this. Okay, let me close with some awkward properties about the normal cones. So when it comes to normal cone, this is very awkward because we require a lot of knowledge. Okay, so back to this board. When you consider general subdifferential, you just want to know, okay, when the subdifferential is non-empty. If the subdifferential is non-empty, then you can just take anything, take any vector and you work with that. But here you have a normal cone and very, very evidently, V here can always be 0x. So a normal cone at the point inside the set C will always be non-empty because it will always contains the 0 vector, 0x. But this is normal cone. It is a cone containing useful directions, the direction making obtuse angles with direction inside C. So if it only contains 0x, or in other words, if it's trivial, then there is no use of considering the normal cone, right? So we need to guarantee in this case not only that the domain of this subdifferential is non-empty, but you have to guarantee the non-zero vector inside this normal cone. And that can be very, 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 very tricky problem. Okay, so I have this problem for you. So let me call it a fact. It's not published, by the way, but I can share with you. So the first one is that if X is in the interior of C, then the normal cone at that point is trivial. It's not so difficult to prove. Okay? If X is an interior point, normal cone is trivial means the only vector inside this cone is 0x. Okay? And in linear space or in manifold, you have this property. The normal cone at X is trivial if and only if X is an interior point of C. So this holds for every Hilbert space, every Banach space, every Riemannian manifolds. But things get very tricky here because I can find an example showing that there is a convex set such that x is not an interior point, but the normal cone is trivial. So this is the underlying this is the underlying and the critical word for me, the final word for me, that when you want to work with this kind of geometry, with this kind of space, with this kind of problem, do not just look for the similarity. Don't always try to imitate what happens in manifold, what happens in Hilbert space, but what you need to investigate, what you need to think more is the dissimilarity. Okay, it has a lot of similarities as you have seen throughout my 4 lectures. But my final word here, I will not show you the example because there is quite complicated, but believe me, there is. So work with caution. Don't always try to prove similar things. Look for the differences. Okay, that is my final word for this course. And thank you everyone for joining. And as I said on the very beginning of my first lecture, if you have anything, just email me, contact CIMPA. Go to my website. I will put a page containing all the details of this lecture as well. So good luck and enjoy mathematics. See you next time.